right? The applied force is going to the right. I have a push on something that is moving, that is either moving across the ground or not moving at all. How do I not, how can I say that it's either moving or it's not moving? Well, if it has a net force, do we know whether it's moving or not? No, we don't. We actually don't know, right? So I could write V is equal to question mark because we don't really know if this thing is moving or not. Friction can keep something from moving. I mean, just try pushing your desk, right, or your table. You may not get it to move, right, unless you put a very, very big force on it. You may not get it to move. Well, there's a force on it, but that means there has to be a counteracting frictional force that is keeping it from moving, right? And so that would be very similar to this situation. Like you pushing on the desk would look something like this. But if you did get the desk to move, but you got the desk to move at a constant velocity, the picture would also look like this, because you would have a force that you were pushing with. Friction would be keeping it from going any faster, but because there would be an equal amount of force in both directions, there would be no acceleration, right? So either one would actually be possible. You could be moving or not moving as long as you don't have an acceleration, right? So A must equal 0 because the sum of the forces equals 0. Okay, look at B. Now in the case of B, you don't have an applied force. Everything else is the same, but you don't have an applied force. So in this case, we do have a net force. It's 5 newtons to the left, right, is our net force. Now, if I don't have a net force, that means that this thing has to have an acceleration, right? Now, we don't know what the mass is, but we do know that the acceleration would have to be to the left. Now, friction is not something that causes motion, it only slows motion. So I would also know that the velocity must be going to the right in this particular case, because if it wasn't going to the right, that'd be very odd for there to be a friction which is slowing it down going to the left, right? That wouldn't make any sense. So the velocity must be to the right. The acceleration, though, is to the left, okay, in that particular situation. In situation C, this could be just something sitting on the ground, right? It has a force of gravity pulling it down. It has a normal force. The surface is pushing it up. And so we know that the net force equals 0 in this particular situation. So it could be sitting on the ground, but it also might be moving. How could something in this situation actually be moving? Think about it for just a moment. Okay, so if you've thought about it for a second, you might have realized that if you've ever been on an elevator, right? If you've ever been on an elevator, if you're on the elevator for a while and it gets a nice constant speed going up or down, you feel pretty normal, right? You feel like your normal weight, right? There are those moments at the beginning and at the end, and we'll talk about those later. There's those moments at the beginning and the end where you kind of feel a little bit heavy or a little bit lightheaded. But in most of the motion, in the middle of your motion, you actually have a net force of 0 acting on you, and you're moving. So we really don't actually know what your velocity is, but we do know your acceleration has to be 0, right, in a situation like this. Okay, in the very last situation, situation D, you have the air resistance. F air is air resistance is actually pushing up on you at a greater amount than gravity is pulling you down, right? Now, how in the world could that be? Well, you got to think about it once again. The sum of the forces is not 0. The sum of the forces is actually 15 newtons up, which means that you are probably falling, right? Because otherwise air resistance would not be pushing you up if you weren't going in the downward direction. So you're falling down, but air resistance is slowing you down, right? Because your acceleration is up. But your velocity must, of course, be down. So if you learn how to read a free body diagram, you can actually determine quite a bit about the situation that something is in. Sometimes, though, you cannot tell what the velocity is, as in situations A and C. You really can't tell the velocity in those situations, but you can tell the acceleration. Okay. All right. Last part here is I want to give you a chance to draw your own free body diagrams. And so I'm just going to ask you to pause this video for a minute, try out each one of these, and then come back to the video and see my explanations of how I would draw a free body diagram for each of these. Okay, pause the video. Okay, if you are back from pausing the video and you've given each one of these a try, let me just real quick draw what these would look like. So you have a book, right? I'll draw it as a box. Again, you could draw it as a dot, right? That would be fine too. So the book is at rest. Well, a book at rest is going to have a force of gravity pulling it down. It's also going to have a normal force, which is holding it up, right? Keeping it from falling. And from what I can tell, those are the only two forces that are acting on the book. Okay, so that's how I would draw that. All right, a crate is suspended motionless from the ceiling by 2 ropes. Well, if I have a crate and it has 2 ropes pulling it up, right, I'll have 2 forces. We'll call it force 1 and force 2, pulling it up. And they are keeping it suspended, so that means that their force has to be equal to the force pulling it down, which is gravity, of course, and they have to be half as big as the force of gravity, right? For this to make any sense. I'm going to put that over here so you can see it a little bit more clearly. So it should look something like that, with the F1 and F2 adding up to be about the same as Fg. All right, let's look at the third one. Egg is free falling from a nest in a tree. Diagram the forces acting on the egg. So let me draw a dot for this one. Okay, we've got gravity, of course. Whoops. We've got gravity pulling it down. And there's probably a little bit of air resistance, right? But probably not a ton, right? It's a round object, fairly dense, probably not a ton of air resistance relative to the amount of gravity. Okay, unfortunately for the egg. And finally, a rightward force is applied to a book. So we got a rightward force, we'll call it an applied force. Move it across the desk with a rightward acceleration. Neglect air resistance. Diagram the forces acting on the book. Well, a book also has mass, so therefore it has a weight, which we call the force of gravity. It also has a normal force, otherwise it would, fall through the desk. And so those should be about equal, right? Or exactly equal, roughly. Not roughly, exactly equal. And there might be a little friction too. But as it says, it's moving with a rightward acceleration, so the friction cannot be as big as the applied force. So I could easily see those 4 forces on that one. Okay, give the rest of the assignment for today a try, especially the worksheet, and I will see you next time.